Learning.
Hi all. This is a joint work with Vidal Alcázar, and well, invariants are known to be useful, right? So why we need a reminder? They are used all the time to generate the FDR representation that most people use. They are known to be almost mandatory if you want to perform efficient regressions, and they are also also been used in other paradigms such as partial order planning or set-based planning. Furthermore, we know several methods to compute invariants. We are not going to propose any new method here. We are just going to use a known method, H2. So the purpose of this talk is to gather some aspects that are somehow known, but they appear scattered in the literature. So many times as side notes or footnotes in several papers. So we want to talk about how to implement these H2 invariants and how to use them in order to simplify the task before starting the search. And the main point here is that this has a huge impact in some domains and can be useful across many planners. So, well, what are state invariants? State invariants are logical formulas that must hold in every state. The usual definition says in every state that is reachable from the initial state. In our case, we use a slightly more general definition, which is a state that cannot belong to any solution path. So this includes not only states that are unreachable, but also states that are dead ends. Okay, and we are going to consider two types of formulas. On the one hand, mutexes, which are pairs of fluents that cannot happen at the same time, pairs of propositions. So for example, an object cannot be in two locations at the same time. And also, we consider exactly one invariant groups, which are set of paths such that as exactly one is true. So basically, this reduces to all the pairwise mutexes and a constraint that says, for example, in this case, an object must be somewhere, cannot completely disappear from our problem. Okay, and whenever we have these state invariants, they allow us to recognize states that are spurious. So states that cannot belong to a solution path, they are either unreachable states or dead-end states. So let me illustrate this with an example. This is the Floortile domain in which we have a grid and a robot, and the robot can move through the grid and paint cells. But it has two restrictions. First, the robot can only paint the tiles that are just up or just down, not at the left and at the right. And the second restriction is that the robot cannot cannot move into any painted cell. Therefore, if our goal is to paint all the cells except for the bottom row, we need to paint them in a particular order. We have to paint them from top to bottom. Because if we paint any cell in the middle, we will have no possible way to paint all the cells above. However, this dead end is not detected by the standard delete relaxation methods because each individual cell can be painted, but not all of them. Okay, the question is whether state invariants can help us in this case. So, as I said, we are going to use H2. This is a standard reachability analysis, so like the H-max heuristic, but considering not only the propositions in our problem, but also conjunction of propositions. So basically, we consider a problem in which our facts are things of the form, the robot is in location 1 and on location 2 simultaneously, or also other pairs could be the robot is in location 1 and the location 4 has been already painted. Of course, this H2 allows us to compute some of these pairs that are unreachable from the initial state. For example, we can discover that a robot cannot be in two places at the same time, but also that a robot cannot be on a painted cell because cannot move into a cell that has been painted. And another remark here is that this does not only allow us to detect states that are spurious that cannot belong to a plan, but also any action that is not applicable in this reachability analysis cannot be part of any plan and can be completely removed from the problem. So basically, that's what we are going to do. We are going to use H2 to detect actions that can be removed from the problem. If you use the standard computation of H2, these actions are unreachable anyway, so they are not going to be applicable during your search. However, this is still useful in other settings, such as if you are performing backward search, you are using abstractions, or you are using other heuristics, because even if the action is not applicable in your problem, your delete relaxation heuristic might think that it is applicable. Okay? This is kind of obvious, but no one has really analyzed what's the impact of doing this in current planners and current benchmarks. Okay, there are some implementation details. As I said, this is somehow known. If you are using strips, you need to consider also the negated proposition. So basically, you need to generate conjunctions that take into account the negation of the fact. So for example, if you have a block work problem in which blocks can become not solid, and you cannot put any block into a not solid block, then this is a mutex. However, if you don't encode the fact that the block is not solid, you will not discover it. However, since we are using the finite domain representation, all our variables are exactly one invariant groups, and we don't need to explicitly represent these negated atoms in this setting. Okay. Another important thing that you can do with invariants is to discover new information about your actions. So, for example, some actions might have some preconditions or effects, some preconditions that are implicit. Look at this example. If in this Floortile problem we add a new action that, for example, paints any location, it doesn't have any precondition, just paints some location for, but also has the effect of making the robot to have low battery. You know for some reason that if the robot has low battery and it's at location 1, it's not going to be able to reach the goal anymore. Then you can add that the robot is not at location 1 as an implicit precondition of this action. Because if you apply this action in any state in which the robot is at location 1, you will only generate a dead-end state. And therefore, adding this precondition can be a useful knowledge. In fact, adding all this information to the actions can allow us to find more mutexes, find more actions that are not really applicable, and also can be helpful for some heuristics. Okay. But the main point is that you can only do H2, the standard H2 heuristic, but you can also do H2 in backward direction, so H2 in regression. This has been already done by previous work, by Peterson and Haslund some years ago, in the context of computing heuristics. But here we are just going to use it to find new state invariants of our task. To do so, it's important that you use the information that you have discovered by applying forward H2 to disambiguate the goal state. So basically, as you know, the goal state might be a partial state and you don't know everything about it. So if you use this extra information, you might discover new things about your goal state. And then you perform H2 in a reverse task in which, well, the goal and the initial state have been interchanged somehow, and the actions have been reversed. So if we, this is actually the reason for which we use this slightly more general definition of a spurious state. Because with this, we are not only going to discover unreachable states, but we are also going to have a powerful dead-end detection method that can be used also for forward search. Okay, so as an example, if we have a task, and we have some trucks that spend fuel when they move, and our goal is to have the truck at some goal location. In the goal state, we don't know how many fuel we are going to have. So we need to assume that in the goal we are going to have any amount of fuel. So all the pairs, the track is at the goal, and we have n fuel, are assumed to be true. But when you apply the regression operator, you know that applying this action, you have waste some fuel. So basically, when you apply regression, you know that the state that leads you to that goal is going to need more fuel than you have. This discovers some useful things, such as I cannot be in any location that is at a distance of 2 from the goal if I only have one amount of fuel, because I am not going to be able to do the 2 moves that I need to reach my goal. So I can detect a dead-end state if this happens. Also, you can remove some actions of your problem. So for example, any action that moves you to that location that is at distance 2 to the goal, if that action has also the effect that it sets the fuel to 1, you can remove the action from the problem, because any state that this action generates is going to be at the end state. Going back to our Floortile example, as I was introducing before, the state on the left is a dead-end state, and we can find it with this state invariance in regression. The reason is that if this is our goal, we don't know where our robot is in our goal state. But since we have discovered, thanks to the forward H2 computation, that the robot cannot be on any painted cell, we know that the robot must be in the bottom row. We still don't know the exact location of the robot, but we know that it's in the bottom row. And if you now apply this H2 in backward direction, you will discover that you can only paint, or in regression and paint, these cells from the bottom. So the paint down actions are completely inapplicable. So of course they are applicable in your problem, but they will always generate a dead-end state. So you can remove them and simplify the problem. You also discover some mutexes. So for every pair of cells that are one above the other, you discover that you cannot have the one at the bottom painted if the one at the top is not painted. So basically, this allows you to detect all those dead ends and simplify the domain a lot. Okay, so what we do in our algorithm is, in the preprocessing stage, we just compute H2 in forward direction. This allows us to find some mutexes and actions that are spurious, that are not applicable. Then we use that information to disambiguate the actions and the goal, finding extra information, and then run the same analysis but in regression. This might find more mutexes and spurious actions, and we can continue whenever we discover something new in regression. We can use that new information to extend our analysis in progression, and vice versa. So we repeat this until a fixed point is reached, and at the end what we have is the set of operators that are not spurious, that are valid operators that can be part of any plan, maybe, and also a set of forward mutexes and backward mutexes that are useful for pruning dead ends in backward search and in forward search, respectively. A side note, even if we disambiguate these actions, we discover more information. We are not including that information in the set of final operators that we use during our search, because for the particular heuristics that we use, we didn't find that it was beneficial. But we believe that there are some other heuristics, possibly these operator content heuristics, that could benefit from that additional information. Okay, so what are our results? We ran this on the benchmark domains. These are the results in the 44 domains until IPC 2011, using the problems in the optimal track for the IPC 2008 and optimal 11. We set a 300-second threshold to compute the state invariance, and this is enough in all except in 3 very hard domains. We discover forward and backward mutexes in a significant number of domains. Especially, there are more forward mutexes that are useful for regression search, but there is also quite a lot of domains in which some dead ends can be detected with this. And in 11 out of 44 domains, this iterative computation until a fixed point is actually useful. And if you look at the numbers for each domain, you can see this is the number of FATs or the percentage of the FATs and of operators that are detected as spurious in each domain. So for example, in Tidybot, we detect that 85% of the operators are really not useful. As you see, there are several domains in which this number of operators is quite significant. So this is really a useful method to simplify all these problems. And if you are worried about these 300 seconds, I can tell you that this computation is really fast in general. So the H2 computation takes 0.1 seconds in more than half of the problems, and under 10 seconds on the huge majority of problems. And all the rest problems are usually not suitable for optimal planning anyway, so current optimal planners are not able to solve them anyway. But this is not only useful for optimal planning. We ran experiments in optimal and satisficing planning. We selected algorithms as simple as possible to illustrate the power of this technique in a simpler setting. We select blind search and LMCAT for optimal planning, and for satisficing, we run fast downward with the FF heuristic and Llama. And as you can see, all the algorithms benefit in the huge majority of cases. Well, this is a selected amount of domains in which they have more impact, but you can see that it improves the total coverage of all the planners, and there is only a few cases in which coverage drops, mainly due to tie-breaking in the FF heuristic. So the conclusion of this talk, I hope that I have convinced you that this H2 invariant computation is very helpful. We have our preprocessor on top of fast downward. We hope to be able to integrate it on fast downward so that all of you can use them. But even if you don't work with fast downward or you want to use another algorithm, I think that it's really important for whatever is your algorithm to use this technique to simplify your problems. In different settings, for optimal planning, satisficing planning, we also tried for unsolvability detection, and it's also beneficial. I really think that that's important to simplify your problem. And well, there are some important implementation details. I hope that our paper can be useful if you want to continue this research and investigate on new methods to simplify the task. So, thank you for your attention.